Hello and welcome to today's video. We're talking about matrix operations today. So you will remember that we have introduced the notion of matrices just a few minutes ago. And of course, we are interested in doing computations with these new objects that we have just defined. Now, one of the easiest operations that we can do on matrices is what we can also do on vectors. And that is, we can add matrices component-wise. Of course, similar to vectors, we could also introduce a component-wise multiplication with a scalar. And that's the two basic operations that we can do for a matrix that we will introduce formally now. So here's the formal definition of those two operations. Let's say we have two matrices that we want to add. So for two matrices, we call those A and B. And of course, both of these matrices need to have the same dimensions so that we can define a component-wise addition. So let's say both are in R to the M times N. And we then define a matrix addition . In the following way. So let A be the matrix whose components are Aij, and the components of B are Bij. Then we define A plus B as the matrix with components Aij plus Bij. And again, that is a matrix in R to the M times N. So in other words, we just add every single component. So what we have here is A plus B is the matrix that we get if we add A11 and B11, A21 and B21, and so on, up to the mth row, AM1 plus B, M1. And we'll do this for the whole row, so in the end, we get first row nth column, so A1n plus B1n. Same for the second row, A2n plus B2n. And of course that goes on up to AMN plus BMN. So this new matrix here, that is the sum of the matrices A and B. And then as a second operation, we can also define a scalar multiplication. So that's part 2 of this definition. For a matrix A with components Aij. Again, we'll assume this is in R to the M times N. And a scalar, let's call that lambda in R. We define a scalar multiplication . In pretty much the same way as we did for vectors in R to the N. So the product lambda times A is defined as the matrix with components lambda times Aij, or in other words, lambda A11 to lambda A1n. And the same thing for every row. So the last row would then be lambda AM1 to lambda AMN. So this defines component-wise addition and component-wise scalar multiplication in the same way as we used to for the r to the n. Let's see just a quick example. So let's say we have a matrix 0, 1, 3, 2, 1, 4, 3, 1. And let's say we want to add another matrix 1, 0, minus 1, 1, 1, minus 2, and minus 2, 1. Then the result of this operation is just component-wise addition. So what we get is 0 plus 1. That's 1. Then we get 1 plus 0. That's again a 1 here. Here is 3 plus minus 1. So we get a 2. 2 plus 1. That's a 3. And so on. So the next column would then be, here we have 1 and 4. And we add 1 and minus 2. So we get 2 and 2. And here we have 3 and 1, and we add minus 2 and 1. So we get 1 and 2. So that's the addition of two matrices. And of course, we can also combine these two operations, scalar multiplication and addition, to get something that is similar to a linear combination. So for example, we could add 2 times this first matrix here to, let's say, 4 times the second one. Again, the convention is that multiplication binds stronger. So you first do the scalar multiplication and then we add the resulting two matrices. And if we do this, well, we get 2 times 0 plus 4 times 1. That's 2 plus 4. It's 4. Here we get 2 times 1, that is 2, plus 4 times 0. Oops, sorry. So 2 times 1 plus 4 times 0, that's a 2. Here we get 2 times 3, that's 6, plus minus 1 times 4, that's minus 4. So 6 minus 4, that's 2. Here we have 2 times 2, that's 4, plus 4, that will be 8. And so on. So the others are, here we have 2 times 1, 4, that's 2, 8, plus 4 minus 8, so we get 6 and 0. And finally, there is 6 and 2, minus 8 and 4, so we get minus 2 and 6. So this is the result of this linear combination here. And indeed, this is actually a linear combination. You will have noticed that basically we're doing the very same things that we did with vectors in R to the n. And of course, we can treat these matrices just as vectors in some R to the n with a sufficiently high value. And of course, basically a matrix with respect to this operation here is nothing else than a very long vector. Imagine you just take all the columns and you write the columns into one very long vector. And then basically the matrix operations are the same thing as the traditional vector operations in R to the n. So what that means is that the space of matrices together with these two operations is actually a vector space. And let's write this down as well. So that is the central theorem of this small section here. First thing I'd like to notice, the space R to the m times n, together with these two operations, so together with matrix addition and scalar multiplication is a vector space. And the dimension of the vector space is m times n. We'll see that in just a minute. That is the second part of this theorem. Of course, we'd like to have a basis. Remember, in R to the n, the simplest basis that we could have is take the all zeros vector, set one of the components to 1, and then we just take all these possibilities, so all the unit vectors, and those form a basis of the R to the n. And of course, we can do something similar in this matrix space. We just take the all zeros matrix, and we put exactly one of the components to 1, and that will yield the basis of that vector space here. So a basis of R to the m times n is given by the matrices. We call those Eij, where I is in m, j is in n. So we get m times n matrices in the basis, and that is why the dimension is m times n. And of course, we have to define these matrices. So Eij is a matrix with exactly one non-zero entry at position row I, column j, and that entry has the value 1. So for example, if we have a look at the R, say R2 by 2, then we have E11 as this matrix here, the 1 in position row 1, column 1. We have E12, where the 1 is in position row 1, column 2, and the rest is zeros. And then we have E21, where we have the 1 here, row 2, column 1. And finally E22, with the 1 being here in row 2, column 2. And you will immediately see that these matrices are, of course, linearly independent, and they are a generator. They span the whole vector space R2 by 2, because you can generate every possible matrix as a linear combination of those 4. So that is indeed a basis, and the dimension of our 2 by 2 is then 4. So this concludes these first matrix operations. In one of the upcoming videos, we'll deal with another more important matrix operation. That is going to be the multiplication of two suitably defined matrices. I'll see you then.